So last time we discussed what is known about quantum field theories in Weitmann axioms, and how from Weitmann axioms you can pass from Weitmann functions to Schwinger functions via analytic continuation, and also how in Euclidean quantum field theory you can try to go from Schwinger functions to Weitmann functions, which is the Osterwalder Schrader theorem. And we saw that this theorem is a subtle theorem, and the current formulations require some knowledge about all endpoint correlation functions in Euclidean, even if you want to rotate just one, say, 4-point function to Lorentzian. It's a bit unfortunate that there is this limitation, and we would like to go around this limitation. And today I'll talk about conformal field theory case, and I will explain how one can overcome this limitation. So in conformal field theory, we will be able to take a 4-point function in Euclidean and rotate it to Lorentzian and show that it has all the nice properties in that signature without ever talking about, say, 6-point or 8-point correlation functions. And so this we will be able to achieve only because of some special nice properties that we have in CFTs, which is the OPE, convergent OPE, and conformal invariance. So this is going to be based now closely on this joint work with Petr Kravchuk and Jiaxin Chao. So what do we need to show? So I'm considering Euclidean CFT, and I'm considering a Euclidean endpoint correlation function. Well, let me take n plus 1 point correlation function of y1, yn plus 1. This is what I denoted curly s. And by translation invariance, this can be written as a function of differences. So I define differences x1, xn, where x1 is just y1 minus y2 and so on. And it is this function Sn that we are going to analytically continue, and I'm not going to modify. We already know from last lecture what is the analytic continuation that we have to do. I'm not going to modify it. I'm just going to modify how I'm going to show that this analytic continuation exists. So we know that what we have to do is that, okay, xi is going to be tau I vector xi. And what we have to consider, that the case where all of these time differences tau I are positive, we have to start from this configuration, Euclidean time-ordered configuration, and we have to analytically continue. Tau I goes into epsilon I plus I ti, where ti is going to be our Minkowski time. And then once we did this analytic continuation, we have to take the limit where all epsilon I go to 0. And we have to show that this limit exists. So how are we going to do this? Well, it turns out, fortunately, that there is a very powerful way to show these kind of things. And what we will have to show is this. We will have to show that this analytic continuation, so suppose that we did this analytic continuation, where we continued times like this. So we will have to show that after analytic continuation, there is a following bound, S of x1, xn is bounded by some constant times some polynomial which can depend on what? It can depend on 1 over epsilon I, and it can depend on the spatial coordinates, so on xi and also the absolute values of analytically continued times. So suppose that we manage to show this bound. So what does this bound say? Well, it says that as you take, roughly it says that as you take the limit epsilon I goes to 0, this function s, which is going to be an analytic function, it blows up not faster than some power of 1 over epsilon. It can blow up, but at most as a power. So this we are going to show. And then just from this result, which seems rather weak, because we only show that something doesn't blow up faster than a power, we will be able to show, we will be able to conclude 3 things. So the first thing we will be able to conclude is that the limit as epsilon I, as all epsilon I go to 0, actually exists and is a tempered distribution. So this is non-trivial. So we start with an assumption that something doesn't blow up faster than a power, but we conclude with something much stronger, that not only does it not blow up, but actually it tends to a certain finite limit, which is a distribution. The second thing that we are going to show is that this function s for all analytically continued times can be written as an integral, which is called Fourier Laplace transform. So s of x1 xn is equal to an integral dq1 dqn of a certain w hat, and here we have e to the minus q0 qi 0 tau I plus I qi vector xi vector. Here we have a sum over i's, where w hat has support at qi0 positive. Now recall that in our last week's discussion, what we did was the opposite of what I'm saying now. What we started with was the Weidmann functions, which had a certain Fourier transform, which we denoted w hat, and then taking this Fourier transform and applying to it this Fourier Laplace transform, we defined Schwinger functions. This is what we did last time. Now I'm claiming the opposite. I'm claiming that given the Schwinger functions, which we will analytically continue, I can find for them this w hat. I can construct w hat such that this equation is satisfied. So I will be able to perform an inverse operation. And once I constructed this w hat, I will be able to say several things. First of all, this limit, whose existence I claim in the first part, is actually the Fourier transform of this w hat. So I can take tau I to 0, and it becomes a Fourier transform. That's the first part. And the second part, which is actually not surprising. So here I only claim that the support of w hat is at positive energies, non-negative energies. But I would actually like to know more. As you remember, in relativistic quantum field theory, the support of Weidmann distribution Fourier transform is in the forward light cone. So I claim that not only as a simple consequence of what I just said, I can show that not only support at positive energy, but actually support W hat is in the forward null cone. So this last part is easy to show. So it basically is a consequence of rotational invariance. So since I know that S from which I started is rotationally invariant, analytic continuation of S is rotationally invariant, given that there is this sort of representation, I can argue that W hat is actually Lorentz invariant because of this interplay tau I, qi, rotational invariance of S becomes Lorentz invariance of W hat. Now, if W hat is Lorentz invariant, in particular, its support has to be a set which is invariant under Lorentz transformations. So the only subset of the positive energy half plane, half space, which is invariant under Lorentz transformations, the maximal one, is the forward light cone. So we know that from here, from this simple argument, that the support actually has to be in the forward light cone. Okay, so this is a bit of magic. So I'm claiming that there is this magic result, that the moment you know the polynomial bound, all of this just magically follows. This is really magic, and I'm going to explain why this magic works. But before I do this, let us just consider a couple of applications. First of all, okay, is the formulation of this magic theorem clear? Any questions? Okay. So let me just do a couple of applications. And the first two examples that I will consider are just the 2-point function and the 3-point function example. Here it's really easy. So I take, for the 2-point function, I start with this expression 1 over x squared to the delta. And then I'm basically saying that what we have been doing all our life, just taking a 2-point function and sticking in I epsilon prescription, is actually the correct thing to do. So relax. You have not made any mistake so far, so good. I'm just saying that what you've been doing is the right thing to do, maybe not so surprising. So we take this formula, which is in Euclidean. Now we take the analytic continuation, which I said. So we got 1 over epsilon plus it squared plus x squared to the delta. And now we send epsilon to 0. This is the epsilon prescription, the usual epsilon prescription for defining Weitman 2-point function. And I just want to say that we know from this theorem that this limit exists and is a distribution. And moreover, it has a spectral function which is supported in the forward light cone. So all we need to do is just to check that there is a polynomial bound, so that this function satisfies the polynomial bound. But this is really easy. So you just have to study this particular polynomial of epsilon, tau, and x and see what it does, what the absolute value does. So in fact, I leave it as an exercise to show that if you take the absolute value of epsilon plus it squared plus x squared, if you take this absolute value, then this is always larger than or equal than epsilon squared if epsilon is positive. So this is always true. You can easily convince yourself that I mean, it's not really automatic, because once you take the absolute value, there could be some cancellations here with epsilon squared minus t squared, so you have to be a bit careful. But this is true. And so if you apply this property, then we know that in absolute value, this the two-point function is just bounded for any x and any t by 1 over epsilon squared to the power delta, epsilon to delta. So it satisfies the polynomial bound, and so the limit exists and is a distribution. Yeah. Yes, I'm assuming that delta is real. Yeah, thank you. Delta is a real number. Because, of course, everything that I'm doing now is only going to apply to reflection positive CFTs, and so deltas are real, unitarity bounds are satisfied, and so on. I'll make some comments about this. Real and positive also. So first of all, real and satisfies also some unitarity bound. Yeah. Yeah. Those are unitary representations of the Euclidean one-dimensional conformal group. But here, when we say that the theory is unitary, we are interested in unitary representations of the Lorentzian conformal group, which actually do not correspond to unitary representations of Euclidean conformal group. This is the usual linguistic confusion which arises. So in reflection positive Euclidean CFTs, deltas are real. Right, it's one dimensional, but you still have to rotate t to it. Yeah. So mathematicians who study, I mean, but it's really easy. Let me try to clarify this. So we are studying these representations. So when I started our lecture, I said, okay, we have to do this representation where Pf of phi of x is equal to 1 over lambda of x to the power delta phi of f minus first of x. This is the formula that I was writing. This was the representation that we are considering. And I was saying that this is a representation that is important for physics. And in physics, delta is the scaling dimension of the field. It's going to be a real number. Now, if you are a mathematician, you don't care that in physics delta has to be a real number. You want your representation to be unitary. What does it mean for mathematicians that this representation is unitary? It means that the L2 norm of phi before L2 norm, just integral of phi, has to be equal to L2 norm of what you see on the right-hand side. Now, if you want this transformation to preserve the L2 norm, delta has to be an imaginary number, because otherwise, because of this rescaling factor, the L2 norm will change. Rescaling normally changes the norm of the function. So that's why mathematicians who are interested in unitary representations in this mathematical sense, preserving L2 norm, they only study imaginary deltas. Well, imaginary with the real part fixed to d over 2. But we don't care that the L2 norm has to be preserved in physics. This is not something that bothers us. So it's unfortunate that what they mean by unitary representation is not what we mean by unitary Euclidean CFTs, but this paradox is resolved if you go to the Minkowski signature.
If you take any correlation function,
Yeah.
real delta,
Yeah.
you pull it expanded on some class of functions, and these functions will be chosen to be the representation of the unitary. Because formally, right?
No, this is not true. This is true only formally. Because no, it's not, because the functions that if you take L2 functions, so I'm saying that these functions that you will get if you're dealing with unitary representations, they are functions which live in L2 space. If you take an expansion in functions which live in L2 space and which converges, you will only get functions which are in L2 space. So if you are interested in functions which are in L2 space, you can expand them in the basis of such functions. You're going to be fine. If you take a physical correlation function in a physical CFT, it doesn't belong to an L2 space, because if you integrate it in x1 minus x2, the integral will diverge. So it cannot be expanded, strictly speaking, in this basis. In some formal sense, maybe it can, but not in a mathematically well-defined sense. I know that you play this sort of games, but you never bother to justify why they're true.
But would you allow me to create the composition of the correlation function? You not worry about the Fourier composition?
Fourier decomposition, I allow you to do this because I'm dealing with.
So you allow Fourier, why do you allow me to do composition of different types of functions and show it to be technical representation?
Well, even the Fourier is a bit. I mean, you weren't here in the second lecture. So Fourier is subtle because we have to know if you want to do Fourier, you have to say what your correlation function does at coincident points. For example, in Lorentzian, we know it's a distribution. You can do Fourier. In Euclidean, you can do Fourier, but you have to tell me how is this Fourier defined at coincident points. Perhaps it's defined by analytic continuation or something. Usually these things are tacitly done. Now, if you want to say that the same thing is true here, you have to develop theory of distributions on the Euclidean group, on the Euclidean conformal group, and then deal with this sort of subtleties. This has not really been carefully developed as far as I'm aware. Now, well, I'm digressing, but this, the fact that there are these loose ends here and there in the literature, sometimes it doesn't matter, but sometimes it matters because people make certain claims and it's not really clear which claims are correct, which claims are not correct. Of course, it would be justifiable if we were dealing with a particularly dirty physical system and we are completely like have no clue what to do, so we take whatever comes our way. But we are not dealing with a dirty system. CFTs are very constrained physical systems. They satisfy rigid rules. So I don't see why we have to cut corners. We can be careful. So what I was doing, so I was saying, okay, there are some subtleties, but in the case of two-point functions, there are no subtleties. What we've been doing with this epsilon prescription is correct. You can try to do the same for the three-point function, and you see that it again works, because the three-point function of x1, x2, we write it as a x1, 2 squared to some power, well, not x1, 2 squared. It's going to be, these are already differences. So it's going to be x1 squared, x2 squared to some power, and x1 plus x2 to some power. And for each of these factors, we have a bound. So this is going to be bounded in absolute value by 1 over epsilon 1 to some power, epsilon 2 to some power, epsilon 1 plus epsilon 2 to some power. So it's polynomially bounded, and the three-point function is also polynomially bounded, and it's hence it is a distribution in a Lorentzian signature. So it's really so simple that it's almost embarrassing. And but notice that it has some interesting consequences. For example, suppose that you really want to know that the spectral condition is satisfied, that once you do this continuation to Lorentzian and you do the Fourier transform is in the forward light cone. For the two-point function, well, two-point function is really simple. You could just imagine doing this Fourier transform explicitly and verify that once you do analytic continuation, the spectral condition is satisfied. But for the three-point function, if you do, this is a non-trivial calculation to do the Fourier transform. You could do it. If you did it, then you would magically discover that indeed the Fourier transform is in the forward light cone. It would be very nice, check. But I'm just saying that it's a consequence of this general theorem. There is no, it's not a surprise. Yeah, they compute. These are formidable computations. They are formidable computations. And if you do those computations, you can try to check the spectral condition, but I'm saying that it's a foregone conclusion that it will be satisfied. So I'd like to explain this magic theorem before going to the 4-point function case. No, it's not obvious. Starting from the 4-point function, it's not obvious. So that's going to be the non-trivial case. Because there we don't have such a simple formula. Any other questions? So let me explain in some detail why this theorem is true. Actually, this theorem is known under the name of Ladinerov's theorem. And so I'll just consider the one-dimensional case, which is sufficiently general. So I'm considering just one function, function of one variable, s of x plus iy. And I'm assuming that it's analytic for x positive. So in the right part of the plane, this function is analytic. And I'm assuming that it satisfies a bound, which I'm going to write as 1 over x to some power. But actually, I also need a bound at large x. So there is a statement about the bound at small x, but also we need to know, and you will see in one step in the proof, that there is some bound also at large x, and there is some polynomial in y. So there's a bound of this type with some constant. And then I would like to show that if I now take this analytic function and if I consider it on some vertical line with real part x, and if I tend it to the imaginary axis, then this analytic function has a limit as a distribution. So what does this mean? It means that if I take integral of s of x plus iy with some test function phi of y dy, then this has a limit, goes to some limit as x goes to 0 for any test function, which is in Schwartz class. Yeah.
I'm sorry, I lost that. Ladinerov's theorem? That's the name of what result?
Ladinerov's theorem is the result which says that if you have an analytic function which at positive real parts satisfies the polynomial bound of this type, then as these real parts go to 0, it has a limit as a distribution, and it can be written as a Fourier Laplace transform. No, it doesn't have to be the same. I'll just pick some sufficiently large R. So we want to show that this limit exists. But again, I would like to say that what does this actually mean? Because you see, if you just estimate this integral by absolute value, it looks like it can grow as 1 over x to some power. So what we are trying to prove is that there are some cancellations going on in this function. Because of analyticity, there are some cancellations which go on in this analytic function. So if there is some place where this function s of x plus iy goes to plus infinity, then somewhere nearby there is some place where it goes to minus infinity, and it does so in some correlated way, so that this integral actually goes to a limit. So that's what's going on. So even though the function in absolute value can grow, in fact there are some cancellations which arrange that the limit exists. So, and if you want to have some intuition about this sort of constellations, you can remember the formula 1 over x plus I0. So this is the Sokhotsky formula, which is the principal value 1 over x minus I pi delta function of x. So there is this formula, which I'm sure you have seen. So you see, the fact that this limit exists is a partial case of, is a consequence of this theorem. And when you define this principal value, 1 over x, this is precisely the sort of constellation that we are talking about. The function is not bounded, but everything is compensated. Plus infinity and minus infinity are compensated. Okay, this is a very special case, but we would like to argue that this is always true using analyticity. And in addition to the existence of this limit, we also would like to write s of x plus iy as a Fourier Laplace transform. So how do we do this? What's the main idea? Well, let me define this, let me call this integral. Let me pick some test function phi, and let me call this integral h of x. It's some function of x. I would like to know what this function does as x goes to 0, in particular that it tends to a limit. So I have the bound just by using this. For the first part of the proof, we only care about small values of x. So we have a bound that h of x is smaller than 1 over x to the r times some norm of phi, some Schwartz norm. Because what we get here is that polynomial times phi, and phi is a Schwartz function, so it's rapidly decreasing, and this decrease is controlled by some norms. And we can pick a norm of sufficiently high order that the integral will converge, will be controlled by this norm, and so we'll get this bound. Constant. So that's not much. So the first key idea is that we can get the bound of this sort, not just for the function h of x, but for all of its derivatives in x. So why is this the case? Well, because if we take a derivative of h of x, so this derivative falls on s, but s is an analytic function, so it satisfies Cauchy-Riemann equation. So the derivative in x of s, I can write it as a derivative in y of s up to I. Now integrate by parts, and I can move this derivative in y on phi. So I now get exactly the same integral, but with phi which is being differentiated. But phi is a smooth function, it's a Schwartz class function. So again, the norms of phi are, the derivatives of phi are again bounded by the same sort of semi-norms. And so what I basically showed is that any derivative of h in x satisfies exactly the same bound with exactly the same power of x, x to the r. Okay, the constant may depend on j, and n can depend on j, but there's going to be a bound of this type. So that's the first step. The second step is to argue is that since every derivative satisfies this bound, it actually magically is going to imply that h tends to a limit. So how does that work? Well, this I can just use the Newton-Leibniz formula. So I can write derivative of order j minus 1 of x as integral of hj dt plus hj minus 1 of first. So hj satisfies the bound 1 over x to the r. So every time I integrate, of course, I'm going to get a bound with the order of singularity which is reduced. So I get that even though I started with the assumption that h j minus 1 satisfied the bound 1 over x to the r, as a consequence of this equality, I know that actually it satisfies the bound with 1 over x to the r minus 1. So I do this, I apply this idea several times, sufficiently large number of times, so that I can completely kill this growth. So instead of getting some bound which blows up in the limit, x goes to 0, I'll get a bound which is a constant. And okay, suppose that I have a bound which is a constant on the derivative, then I write the function as the integral of the derivative. So, well, that integral now converges. So, by this simple trick, I proved that actually the limit exists. So that's how it works. The next thing that I would like to show, that that this function s of x plus iy is actually written as a Fourier Laplace transform. So actually, why do I need it to be written as a Fourier Laplace transform? Because I want to argue for the spectral condition, and for this I need to do this. I need to recover this w hat. So how do I do this? Should I? Questions? So I would like to write s of x plus iy as an integral over d xi of some function g of xi. Well, not function, it's going to be a distribution, e to the minus x plus iy xi. So I would like to show that there exists a temporal distribution g such that this formula is true. So how do I do this? Well, first of all, I take s of x plus iy and I view it as a function of y. Well, as a function of y, it is a distribution. So I can write it as an integral, as a Fourier transform of some gx of xi e to the minus I y xi. Just wrote this function as a function of y as a Fourier transform of some distribution gx. Now, what I would like to show is that this gx can be actually written as g xi. So this gx right now, it has some unspecified dependence on x. But I would like to show that this dependence of x is a very special form. It's actually g of xi e to the minus x xi, where g of xi no longer depends on x. Well, how do I show that? Well, what do I know about this s? That it's an analytic function satisfies Cauchy-Riemann equation. So I just apply the Cauchy-Riemann equation on the left-hand side. I get some differential equation on the right-hand side, on g of x. What is this differential equation? Well, this differential equation turns out to be very easy. It's just g xi is just gx of xi is equal to minus xi gx of xi. So that's the differential equation that you will get. And by solving this differential equation, I know that g of x, gx of xi has to be written in this form with some g of xi. So I'm almost done, but not quite, because so gx was a temporal distribution, but g is related to gx by this exponential factor. And so far, I don't know anything about the support of this distribution. So if I take a temper distribution and multiply it by an exponential factor, I don't get necessarily a temper distribution, but I'd certainly get a distribution that I can integrate with compact support test functions. So I get a distribution. So far, I only know that G is a distribution which can act on compactly supported test functions. So I would like to argue that, in fact, it's a tempered distribution. Well, how do I do this? Well, here what I basically do is that I take this equation and I integrate it with respect to some compactly supported test function on the left-hand side and on the right-hand side. So on the left-hand side, on the right-hand side, I'll get, on the left-hand side, I can take the limit when x goes to 0 because I already proved that the limit existed. And I can show that the limit existed and is a tempered distribution, so I can show on the left-hand side that the limit is actually bounded by some Schwartz class semi-norm. On the right-hand side, I don't know. I get G. I get my G distribution, which is applied against to some test function, and I would like to know that this result. So what does it mean that my distribution, which is initially in D prime, can be extended to S prime? To show this, I just have to show that G acting on some test function phi is actually bounded by some Schwartz class semi-norm. So the difference between a general distribution in D prime and a general distribution on S prime, which is tempered, is that the second class of distribution satisfies this bound. But what I'm saying is that since I already proved that this limit of this S of x plus Iy exists and is a tempered distribution, I get this bound, and so I can show that G, which is initially a distribution in D prime, can be extended to the whole of S prime. So there are some technicalities here, but in the end, I proved that G is a distribution S prime, and so the limit that whose existence I proved is in fact a Fourier transform of G. And well, I guess it's getting a bit technical, but I just have to prove one more thing, which is this claim that the Fourier transform of G is at positive Xi. So I would like to prove that the support of G is at positive Xi. So this is something that I would like to comment on, because this is the only part of the theorem which actually requires to know what happens at large x. Okay, so far, when I was discussing all of these limits, I was just using the value of this analytic function for small x near the boundary of the half plane. But now I am going to use the fact that if I go in the other side away from the boundary, my analytic function grows not faster than a polynomial. So why is this going to help me? Because you see, let me pick some value Xi which is negative. Let me pick some value Xi which is negative. And let me take the limit of where x becomes very, very large. So when x becomes very, very large, this analytic function grows not faster than a polynomial. So its Fourier transform also grows not faster than a polynomial. But the Fourier transform, which is gx, and g are related by an exponential factor. And so if I have something which grows not faster than a polynomial times the exponential factor, which for negative xi is decreasing, you will we get that we conclude that in fact the Fourier transform has to vanish. So g of xi has to vanish. So this is the argument. So I realize that this this must have been a bit formal, but what is the take-home message of this whole thing? I mean, there are two messages here. So the first thing is that well, it's good to know that there is this result that basically saves a lot of headache when dealing with the distributions which are defined as limits of analytic functions. So if you want to show that this limit is a distribution, you just have to study if there is this polynomial bound or not. And maybe the second take-home message is that well, maybe it's a good illustration of how versatile this language of distributions is, because just imagine proving. So in principle, the conclusions of this theorem, they could be formulated without ever talking about distributions. So I just take some smooth function, I consider the integral, and I would like to show that this limit exists for any smooth function. So the conclusion could be formulated without distribution, but the proof, it really uses this distribution technology in some nice way. And if you want to be careful and repeat the proof without ever using the word distribution, I think you would be a bit it would be hard. Yeah. Okay, but now what we are going to do now is that we will use this powerful theorem, and we will try to use this theorem to analyze the 4-point function case in the CFT. So what can we say about the 4-point function? So we go to the CFT and we consider the correlation function of 4 identical scalar operators which, as we discussed, can be written in this form. And so I would like to take this 4-point function, I would like to analytically continue it by setting xi equal epsilon I plus it I xi vector, and in the region epsilon 1 larger than epsilon 2 larger than epsilon 3 larger than epsilon 4. And I would like to see if now, if I take the limit where epsilon goes to 0, this 4-point function satisfies some sort of polynomial bound on how fast it grows. If it satisfies the bound, then I will get a distribution. Now you can say, I mean, why perhaps I can just compute what this distribution is, you could say, because I could just write down some nice formula, because we have seen that in the case of the 2-point function and the 3-point function, we had an explicit formula for 2-point function and 3-point function. You would just do the I epsilon prescription and get some explicit formula for the distribution everywhere except for the coincident points. You could also ask if something like that is going to be true for the 4-point function case. Like we know that the 4-point function is going to be singular somewhere. Okay, there are going to be some light cone singularities, and but what about points not on those singularities? Will we be able to write our 4-point function as some nice formula? So these are all questions that we are going to discuss. So how are we going to do it's important to be systematic about how we're going to do this analytic continuation. In particular, you surely have seen that in CFTs, we love to use these coordinates z and z bar, which are related to u and v by these formulas. U is equal z and z bar, and v is equal to 1 minus z, 1 minus z bar. Now, for me, z bar is not going to be complex conjugation. So I will denote complex conjugation by star. So z bar is just a name, a priori. So you can take these equations. You can take these equations for u and v, and you can solve them for z and z bar. This is some quadratic equation. I'm not going to write them down. But it's important to understand the meaning of this coordinate z and z bar, and one way this can be understood is by taking a 4-point function with which I started, and by applying a conformal transformation which maps 3 points, 1 point to 0, 1 point x3 to 1, well, 1, let's say 0, 0, and 1 point to infinity. And I would like to rotate, I would like to take this point x2 and map it to coordinates x, y, and other coordinates 0. So I can, once I achieved this 0, 1, infinity configuration, I can always rotate this x2 point into the same plane. And so now it has coordinates x, y, 0, 0. So why did I do this? Because now in this configuration, I can easily compute the values of u and v. So as you remember, u is given by x12 squared, x34 squared, divided by x13 squared, x24 squared. So if I evaluate u in this configuration, then I get that this becomes x squared plus y squared. And analogously, v becomes 1 minus x squared plus y squared, as you can check. And so what this means is that in this configuration, z is equal x plus iy, and z bar is equal to x minus iy. So in this Euclidean configuration, two parameters z and z bar are a complex conjugate of each other and are related in this way to the coordinates of the point x2. So that's the first fact that we will need. What is Euclidean, but I'll do the Lorentz in a second. But before I do the Lorentz, let me write down some another useful fact. Is that if we now do the expansion of my correlation function g, so if I write g in terms of z and z bar, then I will have a power series expansion of the form p. So let me call some coefficients p h h bar z to the h, z bar to the h bar. There's going to be some sum over non-negative h and h bar. So what is the meaning of these terms? Is that, remember that we in the first lecture we discussed OPE, and we discussed that this 4-point correlation function can be written, well, it can be written using the OPE, it can be written using the expansion of conformal blocks into conformal blocks. And conformal blocks, they sum up contributions of primaries and their descendants. So we can classify all states appearing in the OPE by their scaling dimension and by their spin. And so, in fact, the term, this term z to the h, z bar to the h bar, corresponds to states of scaling dimension delta, which is equal to h plus h bar, while h minus h bar, it has the meaning. So you see, when we talked about classifying operators in conformal field theory, we had, when we talked about spin, for us spin was related to the representation in which the operator transforms under the whole rotation group in d dimensions. But now when we took this d-dimensional space and we picked in it this two-dimensional plane. So now we can consider two-dimensional rotation group which preserves this plane, and we can classify the states into eigenstates with respect to this two-dimensional rotation group. So this is M12 generator. So h minus h bar is going to be the spin, which is the eigenvalue of the rotation generator M12. So since we are specifying this plane in a reducible representation in d dimensions, is going to split into several representations under M12, and this is the spin. So I'm not using, I could write this sum in terms of conformal blocks, but I don't need conformal blocks for what I'm going to say. So I'm using kind of this whole power series expression in z and z bar. And the only non-trivial claim that I would like to say is that these coefficients p, h, h bar, they are non-negative real numbers. So this is very important. This is very important, and this is not true in any conformal field theory, but this is true in unitary conformal field theory. Unitary, or in Euclidean reflection positive conformal field theory.
Sorry, so you're also claiming that h and h bar are positive, right?
I'm also claiming that h and h bar are positive, yeah. Which is also going to be true in a unitary conformal field theory. Yes, and I'm focusing on analytical operators. So so let me run through the usual, like, I'm not going to be able to justify it fully, but probably some people have seen it, and others will probably get. I'm make sure to make you comfortable. So what is the reason why these numbers are positive? Because I can represent these numbers as norms of certain states which are positive if we are dealing with a unitary theory. So which states are these going to be? Well, I did the OPE of two operators, of the operators x1 and x2, and I consider so x1 is at 0, x2 is at this point y, and I'm doing the OPE, and I'm writing down the terms on the right-hand side of OPE. I'm inserting them again at the point 0, and I'm classifying them with respect to these two numbers, the scaling dimension and the eigenvalue of M12. So I can similarly do the OPE of the points x3 and x4 and insert the result of this doing the OPE at infinity. So since I'm dealing with the 4-point function of identical scalars, these are the same OPEs that I'm considering, just two different kinematics. And so it's the same states which will appear at 0 and at infinity. And so the norms of these states in a reflection positive theory are going to be positive. And then there are going to be some OPE coefficients. And in a reflection positive theory, these OPE coefficients are going to be real. And these numbers P of HH bar, they will appear appear from two sources. They will be products of OPE coefficients squared, which are positive real numbers, times the norms, which are also positive. So this is the general structure of the argument. But now the norms, so there is the subtlety that the condition that the norms are positive, it's a non-trivial condition. In particular, it depends on the dimension of the primary field. So in a conformal field theory, in a unitary conformal field theory, you can show that dimensions of primary fields satisfy lower bounds, called unitarity bounds. And it is that condition that guarantees that the norm of the primary and of all of its descendants, derivatives, they are positive. And so in such a theory, this condition PHH bar is satisfied. So I'm not spending more time about this because this is basically considered to be well understood. So it's it's not mysterious for whoever worked on conformal field theories a little bit. This is well known. While things that I'm focusing on, the Lorentzian things, at least for me, are mysterious. So this is some information. So far, all I said is happening in Euclidean. So Z and Z bar, I'm in Euclidean, so Z and Z bar are complex conjugate numbers. Now I would like to perform analytic continuation. So as Didina asked, my analytic continuation is going to consist to Minkowski, so to Minkowski or to Lorentzian. I take this y and I continue to y plus it. Now, sorry, why do I take y? Well, because I want to keep my points x0, x1, x3, and x4 space-like separated. So I would like to use x as space and y as time. So sorry, before I was like continuing x0, but now I decided to continue y. With just renaming coordinates. So I take y to y plus it, and I plug this into the expressions for z and z bar. So I get z bar equals x plus or minus I plus it. So if I take the limit, y goes to 0, then this goes to x plus or minus t. Minus or plus t, in fact. So we see that in the Lorentzian limit, these two parameters z and z bar, they become real and not equal to each other, but they are related in this way to the Minkowski coordinates. So so then it looks like I can do the most naive thing. I can just take my function g of z and z bar, and I can stick into it these analytically continued values of x of z and z bar, and I can study what happens. So I can study my function g at xt. So this is just g of z bar, where I stick z bar equal x minus plus t. Okay, I also have to analytically continue that prefactor, but that prefactor we already discussed. It's the same as in the 2-point function, the 3-point function case, so it's not complicated. So what can I, so I would like to argue that this is a good analytic continuation, but can I actually do this? So how can I argue that this is a good analytic continuation? Well, I have to have some control of this series in the right-hand side. So G is defined by this series. Now I stick in these different values in the series, but is the series still going to converge? If it converges, then I'm in business. Well, now one way one easy way to argue to see where the series converges is to say, but look, the series has positive coefficients. Z and Z bar are real numbers, so I can just estimate the absolute value of the series term by term. I can say that it's smaller than G of absolute value of Z, absolute value of Z bar. This is obvious, right? So if this series that I get converges, then the one on the left-hand side will also converge. And this is smaller than G of R, where R is the maximum value of absolute value of Z, absolute value of Z bar. So what is the point of this simple game is that what I see on the right-hand side, G of RR, I got back to the Euclidean space. Because if Z equals Z bar, it means that I'm in the Euclidean space where Y is equal to 0. So this thing is again a Euclidean correlation function. So I estimated the continuation in Minkowski space by Euclidean correlation function. So if this Euclidean correlation function is good, then I'm in business. Then my analytic continuation makes sense. But when is this going to be good? Well, it's only going to be good if R is less than 1. So here I need that R is less than 1. Because my series, which defines my Euclidean correlation function, is going to diverge precisely when R is 1. Because if R is 1, it means that the point x2 goes to the point x3, and there my series is going to have a parallel law singularity, and it will diverge. So this simple procedure, which is the simplest one you can imagine, it will work, but it will work only for in the region where Z and Z bar both less than 1 in absolute value. So what is this region? This region is called the diamond. So I have T, I have X, and I continued my correlation function in the Minkowski region to this diamond. So this diamond is interesting. It's interesting. It's not fully trivial, because you see in this diamond I already crossed. I have the possibility to cross the light cone of the point x1. So I know that the light cones are problematic in Minkowski signature, and I'm allowed to cross the light cone of the point x1, but not of any other point, not of the point x3 or the point x4. I could do something similar by using the OP. So here, by using this analytic continuation, I use the OP x2, x1. I could use also the OP x2, x3, and I could then analytically continue my correlation function to this other diamond, which is centered at x3. But by playing this sort of tricks, I will never be able to access the region of space to the future of this point, which is called double light cone singularity. So this double light cone singularity is a mysterious point, and not much is known generally about it. And precisely because it looks like by using this sort of simple tricks, I cannot access it, and I cannot access its future. So in particular, I don't know what my 4-point correlation function does in this area. Like, does it exist there? I mean, what is the formula for this function? I do not know what it is from this argument.
Short question.
Yeah.
So you went continuation to Lorentz.
Yes.
From that moment, I'm asking a question, was time ordered correct? In the video, don't ask the question what was length of time.
Yeah.
So now you take continuation, and now this diamond, I'm asking the question, if I go different parts of the diamond, so create an order different.
Yeah. You're totally right. I was about to say this. So in fact, you see, I can take the limit either from positive y or from negative y. So I'm supposed to take the limit y goes to 0, but I did not say like from positive y or from negative y. So whether I take the limit from positive or from negative y, it defines for me whether I'm considering. So I'm running out of space. Let me say this one thing, and then we make a break. So I'm in Minkowski signature. I am defining Weidmann functions phi of x2, phi of x1, phi of x3, phi of x4, or omega phi of x1, phi of x2, phi of x3, phi of x4, depending whether I'm taking the limit from positive or from negative y. So on the level of the function g of z bar, there is no difference, because the function g of z bar is analytic in this whole diamond. So I can take the limit from y, positive or negative, nothing changes. But there are these prefactors that I said that they are like before. But these prefactors are sensitive to whether you take the limit from positive or negative y. And so you get indeed two different, these two functions are different as distributions. But so you see, we define these two correlation functions, two Weidmann functions, but only in this diamond and only for these orderings, when I am not allowed to cross more than one light cone. So what I will discuss after the break is how you can try to do better, how you can cross more light cones, and how we can try to explore the region beyond the double light cone singularity. Okay. This raw coordinate is it's related to z by a certain formula which I'll just write down like this: 1 minus square root 1 minus z divided by 1 plus square root 1 minus z. And there's a similar formula for rho bar in terms of z bar. Now, why is this an interesting coordinate? Because so z coordinate is nice, but there is something with it which is not quite satisfactory, even in the Euclidean space. So I defined the z coordinate for you before. So it was x1, x3, and x4 to infinity. And so z was this x2 equals z bar. So basically, if you are using z bar in the Euclidean, you are kind of limited to this disk of radius 1 around point x1. But this disk is not the full region of smoothness of your correlation function. So we know that, okay, we expect that the correlation function is going to be singular when x2 goes to x3. But for example, when x2 is here, we don't expect any singularity in our correlation function, right? So, or when x2 approaches this real axis from x3 to x4. So in fact, the only, in a certain sense, the only region where we expect something fishy might happen, but not in the correlation function itself, but in some expansion for this correlation function, is this cut. Well, let me call it cut, but it's not really a cut. So what? So z belongs to 1 plus infinity. So why is this a fishy region? Well, because for any point where x2, say, is on this side of the cut, I can find some sphere which separates x2 and x1 from x3 and x4. It's not going to be centered at the origin, but some sphere exists. And if I move to the other side of the cut, then I will have to change the sphere. So what this means basically is that there is some OPE that allows you to access all the region above the cut, all the way to the cut, and all the region below the cut. But there is no OPE which allows you to access the region on top of the cut. There is no OPE of x1 with x2. There are other OPE channels which allow you to do this, but not x1 and x2 OPE. So we would like to make this explicit, and so we, in order to make this explicit, we introduce this rho coordinate. So the rho coordinate, as a transformation of the complex plane, it does precisely that. So it takes the plane of complex z, which move in C minus the cut, so this region, and it maps it to the unit disk. Absolute value of rho less than 1. So that's one way to guess the rho coordinate. Another way to guess the rho coordinate is this. You can say that, look, this configuration that we are considering, x1, x2, x3, x4, is not a very symmetric configuration, because I somehow chose by fiat that I put x1 to 0, x4 to infinity, but the point x3 and x4, x3 and x2, they are not really symmetric. So why did I put x1 to 0, not x2? Can't I do things in a more symmetric way? You can do things in a more symmetric way. And to do it, you can choose another frame where you, instead of fixing points like I did, I'm going to fix them in a different way. I'm going to fix 2 points to -1 and 1, symmetrically with respect to the origin. And then 2 other points, I will also try to arrange that they're symmetrically with respect to the origin. Let me try to find such a configuration of points. And it turns out that if I do this, I can do it. I can find such a conformal transformation. Then these 2 points are precisely going to be fixed at rho and minus rho. Complex. So if we are in the Euclidean, it's going to be complex value of rho, and rho bar is going to be, again, complex conjugate of rho. So that's another meaning of this coordinate rho. And this coordinate rho, it shares with the coordinate z this property that if I now take the function, and instead of writing it as a power series in z and z bar, I transform it to rho and rho bar, it's going to have a power series expansion, some other coefficients, q, where q are going to be different coefficients, not the same coefficients as p, but again they're going to be positive. Rho to the h, rho bar to the h. And again, this is very well understood, positive in unitary theories, and the explanation is again the same, that I can surround I can surround my my 2 points by a sphere, and I can consider these q's again as some p coefficients times norms of some states which have to be positive. So this is true. And so you see, basically, q is this raw coordinate is a very close relative to z, but it's more powerful. And now I can try to say, okay, I mean, let me just try to run the same argument that I did with z, but in terms of q, in terms of rho, sorry. So instead of analytically continuing this z series, I'm going to analytically continue rho series. So what does it mean? Well, it means that I take, of course, I start by analytically continuing z and z bar, like I wrote there. But now for z and z bar, let me compute the corresponding rho and rho bar. And let me check the condition. So the condition that I will have to check is that rho, absolute value of rho, and absolute value of rho bar are less than 1 after the analytic continuation. So let me repeat. I take z, I analytically continue them, I compute rho, and I check that condition, rho bar less than 1. If
Is it evident? Do you need that Q are positive? Because it's more evident that Q are positive.
I need that Q are positive, because if it's not positive, I cannot argue. So you see, the magic, my argument was that in Euclidean space, I know my correlation function, and I know that it's bounded, I know that it blows up only at coincident points. And I want to argue that anywhere else, in particular in Minkowski, correlation function is bounded by the Euclidean somewhere, and so it cannot blow up. But for this to be true, these coefficients q must be positive, or p, because if they are not positive, then there could be some phases or which could make it in such a way that the Minkowski correlation function is going to become larger than the Euclidean correlation function, and then the argument doesn't work.
It's not evident that it's a linear combination from P.
Yeah, but you don't argue that Q are positive expressing them as linear combinations of P's. You argue that Q are positive by using an OPE argument in this frame. Okay, so it's more robust.
Even if they are not positive, couldn't it work if just to have a absolutely convergent series?
Yeah, okay. You could, even if they are not positive, you have to say something about this series where you take them in absolute value. And you have to argue that the series converges. But how would you argue that? My way of arguing for that is to say that this series is actually a correlation function, and we assume that all correlation functions are finite. If we just have some other series where I start taking things in absolute value, I don't know the physical meaning of that series, so I cannot argue if it's finite or not. It's hard, at least. So then the argument breaks down. So that's why, for example, in non-unitary theories where these coefficients are going to be not necessarily positive, it's much more subtle. So yeah, so you say how am I going to argue? So right now I'm considering the case of identical operators, but as Monica points out, I am of course interested also in knowing that correlation functions of non-identical operators are distributions. So how would I argue that? Well, that's a very easy that's a very easy consequence of the positive operators, because if I have non-positive operators, so I consider it's a well-known trick. So you instead of taking them all different, let me first of all consider the operators when they're pairwise equal, like phi 1, phi 1, phi 2, phi 2. Then I apply Cauchy-Schwarz inequality, which says that phi 1, phi 1, phi 2, phi 2 is bounded by phi 1, phi 1, phi 1, phi 1 times phi 2, phi 2, phi 2, phi 2. But that case I already considered. So this way I consider this other case. But then, as you can imagine, doing the same trick once again, I'm considering, I'm showing also the totally general case. So but what's going to happen now? Well, in principle, I'm so what should I study? I should study when can this happen. So this is the condition that I have to look at. Rho bar is less than 1. Well, let me just look at rho. Rho is some function of z. So I have to understand when can it happen that rho approaches absolute value 1. Well, it can only happen if z approaches the cut, because all other points on the plane are mapped inside the unit disk. It's only the cut from 1 to infinity is mapped on the boundary of the unit disk. So in order to show or to understand that rho is less than 1, I have to understand whether z ends up on the cut. But now let me look at my z and z bar. Z and z bar are x plus or minus t, so they're actually real. So for them to be not on the cut, I have to impose the condition that x plus minus t is less than 1. So now compare it to the previous condition that we had. Previously we had a condition that absolute value x plus it, x plus or minus t, was less than 1. That was the condition that we got using z and z bar. Now using rho and rho bar, we got a more relaxed condition which just imposes something on the absolute value, on the maximum of x plus or minus t. Now, what does this mean? What does this imply? It implies that by using this trick, I can continue analytically my correlation function to a bigger region, which instead of being a diamond, now I can cover this whole wedge. Which is to the left. And by doing similar argument with the other OP channel, I could consider this part to the right. So you see, I'm making progress, but I'm not yet able still to access the double light cone, singularity and the future. So I'm not fully solving the problem. So, well, actually, there is one more technical detail that I am not discussing here, but I hope that you will believe me. So I only showed you that given that this condition x plus minus t is less than 1 is satisfied, I'm not on the cut. This as much as I showed you. But now suppose that so this was the condition true when I already sent y to 0. But here I am neglecting one point. So what I had to show is that so I had to get, in order to apply Vladimirov's theorem, I had to use a polynomial bound on my analytic continuation in terms of the original coordinates, which are x, t, and epsilon. But if I'm using this rho bar argument, I'm getting a polynomial bound in terms of rho and rho bar. So strictly speaking, what I have to do is that I have to study how rho and rho bar depend on z and z bar through this formula. And to show that polynomial bound in terms of rho and rho bar actually implies a polynomial bound in terms of coordinates x, t, and epsilon. But you will believe me that that looks very plausible, because given that rho is given by some algebraic function of z, you know, the fact that z cannot approach, the fact that rho cannot approach 1 faster than a polynomial probably implies that z also does not approach 1 faster than a polynomial. So this is a technicality, but I have some notes on that. You can check them out. So what remains then to be done? Well, first of all, I have to come up with some argument which covers the future of the double light cone singularity. But even in the situation that I'm not beyond the double light cone singularity, there is something that I have not quite achieved yet. So you see, I'm so far considering just analytic continuation in one coordinate, x2. And I keep all the other coordinates fixed. But strictly speaking, I have to consider analytic continuation in all coordinates, x1, x2, x3, x4. So if I do this, then clearly there are going to be many more possible permutations of various points becoming time-like separated from each other that I have to consider. So if I just consider x2, then okay, x2 can be time-like with respect to points x1 and x3 and so on. But imagine now I'm starting to continue all of these points. I have to say, okay, x1 is time-like with respect to x3, but x2 is time-like with respect to x4, and what is their time-like separation? So it looks like a total mess. There are lots of combinatorial situations that you can write down, and somehow I have to be able that in all of the situations, my function is under control. So this looks like a formidable task, but I claim that I can do this. And so how am I going to convince you? So let me do first the 2D case, and then I will explain how to do the general d-dimensional case. So let me now do general 2D case. What does it mean, general? It means that I'm not going to fix any of my points to some particular configurations, but I'm just going to consider x1, x2, x3, x4, and I'm going to analytically continue in all of these coordinates. And I would like to study what's going to happen with this analytic continuation. So how can we achieve this? So I'm doing analytic continuation in all of these coordinates, but and then I would like to use the formula in terms of z and z bar, or maybe the formula in terms of rho and rho bar. If I want to use the formula in terms of rho and rho bar, I have to compute rho in terms of z, and I have to somehow express z, which corresponds to the analytically continued 4-point situation, in terms of the coordinates of the points. The beauty of the 2D case is that I can write down, even though I'm analytically continue in all of these coordinates, I can write down a general formula for the parameter z, in terms of the coordinates of all of these points. So let me write, suppose that x1 is equal x, so I'm going to write x1, y1, I'm doing some math with notation. So the point is that, okay, I have four coordinates. Let me first of all consider that all of them vary in the two-dimensional Euclidean plane. So each of these four coordinates I'm going to parameterize by complex numbers z1, z2, z3, z4, which is just a complex coordinate in the plane, and z bars. Now I'm asking the following question. So I have four coordinates moving around. Let me now move these 4 points into this configuration that I was considering, 0, 1, infinity, and the point. And what is going to be the value of z that I will find? So the claim is that z is equal z1 minus z2, z3 minus z4, divided by z1 minus z3, z2 minus z4, and similar formula for z bar. In other words, for every configuration of 4 points, there is some value of z and z bar, and it's some complicated function, in general complicated function of coordinates. But in 2 dimensions, this function is not complicated at all. I can compute it very easily. I just write down everything in complex coordinates, and this is the value of z. So why does this work? Well, you can just check that this works, because we have to check these values z and z bar that I gave you. They satisfy equations z bar equals u, and 1 minus z bar equals v, which are functions of xij. And in 2D, this is indeed true. Maybe you know other better proofs of this fact, but you can do it completely explicitly. So this is already a big advantage, because now if I have an explicit formula for z, I can hope to do something with it. I can hope to show that it doesn't touch the cut, and then if it doesn't touch the cut, then I will compute rho, and rho is going to be less than 1. So this is the general strategy. So now I take this z, and I introduce these variables zeta1, which is equal to z1 minus z2, zeta2, which is equal to z2 minus z3, and zeta3 is equal to z3 minus z4. And I rewrite z in terms of zetas. So what do I get? I get z is equal to zeta1, zeta3 divided by zeta1 plus zeta2, zeta2 plus zeta3. And I'm going to write it as 1 divided by 1 plus zeta2 over zeta1, 1 plus zeta2 over zeta3. Okay, so this is the formula in Euclidean space, but now I can do analytic continuation. So my analytic continuation is going to be, so zeta I, which in Euclidean space is xi plus I yi. So this goes into xi plus I yi plus ti, which is equal to ITI, sorry, which is equal to, let me call it AI plus I yi, where this is x minus t. And now I have to take the limit where all of these yi's, which are positive, and they go to 0. So this is the analytic continuation that I have to perform. And if I do this analytic continuation, then I'm going to define a correlation function, Whiteman correlation function, phi x1 t1, no, sorry, phi 0, 0, phi x1 t1, phi of x1 plus x2 t1 plus t2, phi x1 plus x2 plus x3, t1 plus t2 plus t3. In this ordering. But since my times are completely arbitrary, t1, t2, t3 arbitrary, it means that I'm going to cover all possible time orderings of operators. Of course, if I can show that the limit exists. So now something magic happens that I would like to point out is that this function, so you see, these zetas, they vary over the upper half plane. So AI is a real number, and the imaginary part is positive. So I have a function from the upper half plane, well, actually 3 copies of the upper half plane to complex numbers. It's this very particular function that I wrote. For our strategy to work, I have to check whether, so the crucial question is that so there is this function z which maps zeta1, zeta2, zeta3, which belong, each of them belongs to the upper half plane. So it's like h cube, and maps to complex numbers. And we know that there is this problematic region, which is the cut. Z belongs from 1 to infinity. So we would like to know, when I take this function, applied to the 3 copies of the upper half plane, am I going to end up sometimes on the cut or not? If I end up on the cut, then well, then it's not. Then I'm not. That I'm not in business. If I don't end up on the cut, and if I approach the cut, if I can only approach the cut somehow, but not cross it, then using the row variable, using the argument in terms of the row variable, I'm going to prove that my function satisfies the polynomial bound, and hence the analytic continuation is going to be a distribution. So now something magic happens is that this function, you compute this z, and you find that it never crosses the cut. Well, there is no simple formula. Well, I could give you a proof, but the proof is basically by inspection. You like say, okay, I know that so this is a function of zeta2, zeta1, zeta3. Let me fix some zeta2 in the upper half plane. Let me vary zeta1 and zeta3 also over the upper half plane. And let me see how can this happen that this number ends up on the cut. Well, you can, for example, pose the first question is whether this number can be real or not. You impose this condition that this number is real, and you will find that if it's real, then it can only lie at z less than 1, but not on the cut. So it never approaches the cut. Okay, so well, let me actually go back to the previous case when I was still continuing just one point, x2, because there is something that I forgot to stress. So actually one very important point that I forgot to stress. Maybe that's going to be the last thing I will say today. So you see, I had these two variables, z and rho. And I had this problematic region to the future of the double light cone singularity. So if I was using the z variable, then this problematic region was like totally inaccessible, because in the problematic region, the variables z and z bar, they are really larger than 1, so the series that defines the 4-point function completely, like, it's totally not under control. Now, if I now go to the rho variable, what happens? So if I'm in this wedge, or then the rho variable and the rho bar variable, they are strictly less than 1. So I know my correlation function here is analytic up to this prefactor, 1 over x12 squared up to 64 squared. But the function g is here is analytic. If I now go to the double light cone singularity and its future, then I'm on the cut. So it means that rho and rho bar are absolute value 1. So the series naively is not under control, but it's just barely not under control, because it's not like in terms of z variables and z bar variables where they are larger than 1. It's rho and rho bar is absolute value 1 exactly. So in this whole region to the future of the double light cone, rho has absolute value 1. Well, because we know this, right? So we know that here, z and z bar are x plus or minus it, right? So if they are here, z and z bar, z or z bar, are larger than 1, it means that they're sitting exactly on the cut. But the cut corresponds to rho being absolute value 1. So what I'm saying is that we are actually, so what does this mean? It means that even though here we cannot argue that the series converges, if we go a little bit away from the cut, rho and rho bar becomes less than 1, the series converges, we can use the bound, and now we just have to show that as we approach the cut, the function grows not faster than a polynomial, and then by Vladimir's theorem, we know that on the cut, the function is a distribution. So in fact, by what I already said concerning this relation between z and rho variable, I proved that in any conformal field theory, if I continue my function, my 4-point function, to the region around the double light cone singularity and to its future, it is a distribution. So this is something that I have already proved. Now, this, it's interesting. So now that we know that this function is a distribution here to the future of the double light cone, you can ask, okay, well, is it a distribution, but is it something singular? Is it really like a real distribution, you know, maybe like a delta function or anything? or maybe is it a smooth function actually? So that's something that's a question that you can try to study. Now that we know that it's a distribution, we know how to define it, we can study what is the structure of this distribution to the future of the double light cone singularity. And in fact, in two-dimensional CFTs, you can show that we're using a different argument that to the future of the double light cone singularity, this distribution is actually a smooth function. So in the two-dimensional CFTs, you can show that all singularities are on the null cones, on the light cones, but the moment you move away in the bulk, the distribution there becomes actually a smooth function. But in three-dimensional CFTs or in four-dimensional CFTs, I don't know of any proof concerning this fact. So in fact, it is a possibility that if you take like some three-dimensional CFT, like three-dimensional Ising model, and we analytically continue to the future of the double light cone singularity, there we will find some crazy singular distribution. So it's an open question what happens there. So I completed that discussion, and this discussion concerning the general 2D case, I think I will have to pick it up next time. So basically, the plan for the next time will be to finish this analytic continuation in the Minkowski space, in the flat Lorentzian space, in 2 dimensions, and then I will explain how it works in general D dimensions. So this will show for the first time that the 4-point function in any reflection positive CFT actually satisfies Weitman axioms in Lorentzian for all possible time orderings. And then I will, for the rest, I will spend some time discussing other famous Lorentzian space-time associated with any CFT, which is the Lorentzian cylinder. So if you know ADS CFT, it's the boundary of ADS space. Lorentzian ADS space is the cylinder. And so there is a famous paper by Lusher and Mack, who tried to analytically continue correlation functions to the cylinder. And in fact, most people believe that they did continue to the cylinder, except that they say explicitly that they did not. They did not manage to do this in their conclusions. So I will. So this is kind of another like famous unfinished story of this CFT, and using the same sort of technology that we developed for the Lorentzian flat space, I would like to explain how to clean up that story and to show that indeed the correlation functions of CFTs can be extended to the Lorentzian cylinder, and what is the structure there. Enough for today. Yeah.
What about winning the presentation?
What about it?
What you're proving here? Isn't equivalent to proving the correlation function needs no presentation?
Is it equivalent?
But if I started with Miller's representation, all the question about what continuation is equivalent solved.
Well, I know what you're referring to, but I disagree with trivially and with solved. So there are some explicit calculations that you can try to perform using the Miller representation, and they have been performed. But that's I don't know of a general argument that this procedure works in general, because you would have to justify that Miller representation exists for any conformal field theory correlation function, and I'm not aware of any general results of that kind. I mean, sometimes you can exhibit by an explicit calculation that this Melian representation exists. If you know, for example, explicitly correlation function, you can try to do this Melian representation in Euclidean space, and you can try to use this then to construct continuation to Minkowski space. In those lucky cases, that would be just an alternative way to construct an analytic continuation, and since analytic continuation is kind of unique, it would agree with the analytic continuation that we are constructing here. But I don't know how to argue it in general. So this Melian representation in CFT, it's another murky subject that I think it would be nice to fully explain, like when it exists, what is the structure, and so on. Yeah. But I would be happy to discuss what is your point on this.